Hello everyone and welcome. In today's video, we're going to continue with our treatment of L'Hopital's rule, and we're going to look at indeterminate powers. We are going to learn how to evaluate limits involving indeterminate forms of the type 0 raised to the 0th power, infinity raised to the 0th power, and 1 raised to the infinity. And you might be wondering, how come infinity over infinity or 0 to the infinity are not indeterminate? And we're also going to talk about that. We're going to talk about why these are indeterminate, whereas these are determinate. So we'll also reason about that. So to get started, let's suppose that you're working on a limit question of the following form: the limit as x approaches c of f of x raised to g of x. And when you're solving these limit problems, several indeterminate forms can arise. So you can have an indeterminate form of 0 over 0, which is when both the base and the exponent approach 0, it leads to this indeterminate form. Or if the base approaches infinity and the exponent approaches 0, it leads to this indeterminate type, infinity raised to 0. And lastly, if the base approaches 1 and the exponent approaches infinity, then you get this indeterminate type of 1 to the infinity. So we'll discuss why these are indeterminate at the end of the video. For now, let's just learn how to evaluate this indeterminate type if you come across it. So there's two methods that you can use to evaluate these limits. They both rhyme a lot and essentially you're doing the same thing. So for the first method, you want to use the fact that e and natural log are like inverse functions. They undo each other. So whenever you have sort of some input, you can do e natural log of that input, right? And those e and natural log cancel and you get back to your input. So we're going to use this sort of identity. So let's begin by writing down the limit as x approaches c of f of x raised to g of x. And then I am going to use this identity. I am going to write e natural log and then pass that input there, f of x and g of x. Right? So these will sort of cancel out and I should get back here. Now I will use one of the properties of the logarithm to bring the exponent down and we get this form here. So to evaluate this limit, we have to understand the behavior of this exponent. That is, we gotta compute this limit. And so if this limit exists, by the continuity of e to the x, you can just pass this limit sign up here and get your answer. So whatever this limit evaluates to, let's call it L, then the value of the original limit is e raised to the L. And here's the thing, if you're working with an indeterminate power, like 0 to the 0 or infinity to the 0 or 1 to the infinity, then it turns out that to evaluate this limit, you will actually be working with an indeterminate product. You will always have something like 0 times infinity. Now, the second way to write your solution is to define y to be f of x raised to g of x. Okay, so call this power y, right? Y is a function of x. And so the goal is to compute the limit as x approaches c of this function, right? In other words, the limit as x approaches c of just y. That's what we have to figure out. Now, what we're going to do is we're going to apply the natural logarithm on both sides, just like this. And then we're going to bring the exponent down, just like we did over here. And now, instead of computing the original limit of y, let's compute the limit of ln of y, the natural logarithm of y. Okay, and so to do that, we just have to take the limit of this expression. And does this expression seem familiar to you? Yeah, in fact, it's actually just this expression here, right? So that's what I'm saying. These two methods rhyme a lot. So you have to evaluate this expression. Now, if the original limit is an indeterminate power, then this will always be an indeterminate product of type 0 times infinity, and we discussed how to evaluate stuff like that. Now, assuming that this limit gives you an answer, let's call it L, right? Then it turns out that you can compute the limit of the original function y, because y is just e ln y, right? Y is just e ln y. So you can replace this y with this other representation, e ln y. And now we apply the same idea. E to the x is continuous, so you can just pass the limit sign through. And you are evaluating e to this limit that you found. E to this limit is what you're evaluating. And so a few things I want to highlight here is that this continuity of e to dx is important. Okay, you cannot just pass limit signs wherever you want. Here it's completely justified because e to the x is a continuous function, and so it's completely valid to move e to the x here. And the other thing I want to mention here is that to evaluate these limits, the original limits that we care about, we basically have to work with this indeterminate product, right? We want to work with this sort of a limit here, as you can see. The key is really solving that product. So now let's take a look at some examples to see how these approaches work. Okay, so here's the first example, and here I just want to show you how to write your solution. Try to understand the steps on how I'm writing the solution, because this is how you want to write your own solution. So let's suppose we want to evaluate the limit as x approaches 0 from the right-hand side of x to the x. So the first thing you should do is determine the behavior of what happens as you approach 0 from the right-hand side. Well, clearly the base is going to go to 0, and the exponent will also approach 0. So this is an indeterminate power of the form 0 to the 0. Now, in a previous video, specifically in the indeterminate products video, we actually computed this limit here. Okay, it's pretty easy to compute. We can do that. But again, that's not the focus. I just want to show you the format on these two approaches just so you see what the differences and similarities are. But yeah, let's just take this as given. The limit as x approaches 0 from the right-hand side of x ln x is equal to 0. Okay, you'll see where this comes in. So let's get started with the first approach. In the first approach, you write the limit as x approaches 0 from the right-hand side of x to the x. Then you use this trick. You want to sort of write this as e ln of that function, right? Because these sort of cancel and you'll just get back here. Now you want to use the property of the logarithm to bring this exponent x down, just like so. And then by the continuity of e to the x, you want to push this limit sign into the exponent, just like that. And so you can see that in order to evaluate the original limit, we need to be able to solve this limit, this sort of product. And so in this problem, it's given to us that the limit is just 0. And so as a result, the final answer is e to the 0, which is just 1. So the limit just evaluates to 1. This is why I like this method. The first method is pretty clean to write out. Just a few equal signs, and you go on the side and you just compute this. Okay, we'll do some full examples after this, but you just go on the side of the paper, you compute this, plug it back in here, and yeah, your solution looks very clean. And now let's take a look at how you would write this solution using the second method. So the first thing you would do is call x to the x y. So y is equal to x to the x, which is the function in question. Then take the natural logarithm on both sides of this equation, just like so. Then apply the property of the logarithm to bring this exponent down to get this. And now, instead of computing the limit of y, which is what we care about, right, the original limit, what we're going to do is compute the limit as x approaches 0 from the right-hand side of the natural log of y, which is exactly this expression, right? So the limit as x approaches 0 from the right-hand side of x ln x. And again, this is for now given to us as just 0. But over here, you would stop and go on the side of the paper and compute this just by using L'Hopital's rule and techniques we covered about indeterminate products. But yeah, once you do that, you get 0. Now, to find the limit that we care about, which is the limit as x approaches 0 from the right-hand side of y, you realize that y is just e ln y. And we have the value of this. We know how this behaves. This approaches 0. And so that's what's going on here. We're passing the limit sign through. This is possible by the continuity of e to the x. And so we get e to the 0, which equals 1. And so yeah, very, very similar methods. You can use either or. I personally prefer this one. It's a little bit more cleaner. But this is sort of how your solution should look like. Now let's take a look at some full examples where you have to compute also this intermediate limit. For the next example, we're taking a look at the limit as x approaches 0 from the right-hand side of 1 plus sine of 4x, all of this raised to cotangent of x. So a pretty complicated looking limit. So the first thing you should do is try to plug in 0 to see how the base and the exponent behave. In this case, when you plug in 0, sine of 0 is just 0. So the base is approaching 1 plus 0, which is just 1. The base is approaching 1. Now the exponent cotangent is just 1 over tangent. And we know that tangent of 0 is 0. As a result, 1 divided by a very tiny number is going to approach infinity. So we have the exponent approaching infinity. So this is an indeterminate power of the form 1 to the infinity. For this problem, I'm not going to show both approaches. I'm just going to use the first approach, but you're welcome to write the solution yourself using the second approach to practice. So using the first approach, we're going to write the original limit down, and we're going to take e ln of that limit. And I'm going to skip one step. I'm also going to bring that exponent down. So that's what I've done here to get here. I've taken e ln of the entire function, and then also brought the exponent down in the beginning to get this. And then by continuity of e to the x, you can just bring this limit to the exponent. And so the goal now is to evaluate this limit. So let's go on the side and evaluate it. So we want to focus on the limit as x approaches 0 from the right hand side of cotangent times the natural logarithm of 1 plus sine 4x. So as x approaches 0, cotangent, as we discussed, is going to approach infinity. And then we know that the inside is approaching 1. And natural log of 1 is 0. So this is an indeterminate product of the form infinity times 0. Now we discussed in a separate video how to handle indeterminate products. The idea is that you want to bring one of these functions down. In this case, I want to bring the cotangent down. So I'll be dividing by the flip of cotangent. But 1 over cotangent is exactly the regular tangent function. And so we get this limit. Well, now when you plug in 0, then the top is going to approach 0, and so is the denominator. The denominator is also going to be approaching 0. So we have successfully converted an indeterminate product into an indeterminate quotient. Now let's apply L'Hopital's rule and differentiate the top and bottom separately. To differentiate the top, we have to use some chain rule. The derivative of natural log is 1 over the input. The input is this function here, so we put that there. And then by the chain rule, we have to multiply by the derivative of this input, this inside function. And the derivative of 1 is just 0. And the derivative of sine is cosine. Then you keep the inside the same, and you chain it with the derivative of the inside, which is just 4. And that's how you get this. And then the derivative of the denominator, which is tangent, is just secant squared. Now let's try to evaluate the limit. So for the denominator, we have 1 over cosine squared of 0. Cosine of 0 is just 1. You square that, you get 1. 1 divided by 1 is still 1. So yeah, this bottom just evaluates to 1. Now for the top, we have sine of 0 is 0. So this is just 1 plus 0, which is just 1. All of this is just going to be 1. Now cosine of 0 is 1 times 4 is just 4. So we have 4 on the top. So we have 4 divided by 1 divided by 1. The answer is just 4. Now you take this limit and you just plug it back where we came from. And the final answer is just e to the 4. Great, let's take a look at one more example. In this problem, we have the limit as x approaches 0 from the right hand side of x raised to the sine x. So first let's analyze the behavior of the base and the exponent as we approach our limiting value of 0. Well, as x approaches 0, then the base is going to approach 0. And then sine of 0 is also 0. So the exponent is also going to approach 0. So we have an indeterminate power of the form 0 raised to the 0th power. So as we discussed before, we're going to begin by writing the original limit. And then we're going to use the e ln trick. We are going to write this as e natural log of the function x sine x. And then you want to bring the sine x down. So I did 2 steps in one to get to this step here. Now, by the continuity of e to the x, you can just bring the limit sign inside, and we get this. And now our goal is to actually evaluate this product, right? The limit as x approaches 0 from the right-hand side of sine of x times ln of x. So let's go ahead on the side and do that real quick. So as x approaches 0 from the right-hand side, sine is going to approach 0. And then natural logarithm is going to approach this asymptote. So it's going to go to minus infinity. So we have an indeterminate product of the form 0 times minus infinity. So to convert this indeterminate product into an indeterminate quotient, we have to decide which function to bring down. And usually you want to bring the trigonometric function down because when you flip the trigonometric function, you get another trigonometric function. You're going to get like a reciprocal trigonometric function. So let's do that. Let's divide by 1 over sine x. But 1 over sine x is exactly cosecant x. So we get to this step. Now let's analyze the behavior. As we approach 0 from the right hand side, natural log of x is going to approach minus infinity. Cosecant x is going to approach infinity because cosecant is just 1 over sine, and we're plugging in 0, right? So sine of 0 is 0, and we're approaching 0 from the right hand side. So it's always going to be a very tiny positive number. 1 divided by a very tiny positive number is going to be a very big number. And that's why you got infinity. Now we're allowed to apply L'Hopital's rule. Let's go ahead and differentiate the top and bottom separately. The derivative of the numerator, natural logarithm, is just 1 over x. The derivative of cosecant is actually negative cosecant cotangent x. Now let's try to simplify this a little bit. So I want to bring the cotangent up and the cosecant up. When I do that, they're going to switch into the primary forms. So I'm going to get sine x and tan x. And then I want to bring the x down so we have x in the denominator. Just in case if you didn't follow why this flips up and becomes tangent, you can think of this as 1 over tangent. And then dividing by a fraction is the same thing as multiplying by its flip, right? And so that's where you get the tangent from. You can apply the same idea over here with the cosecant. Cosecant is 1 over sine. So then you multiply by the flip. And that's another way you can get your sine x on the top. Now we can do another simplification here before applying L'Hopital's rule, which is that tangent is sine over cosine. So then we can bring the cosine down and then multiply the sine and sine together to get sine squared and then cosine on the bottom. And now let's try to evaluate this limit. As you approach 0 from the right hand side, sine is going to approach 0. So sine squared is also going to approach 0. And on the bottom, it's also going to approach 0. We have this x factor up front. So this is an indeterminate quotient, and we can apply L'Hopital's rule. We have to differentiate the top and bottom. To differentiate the top, we will use the chain rule and the power rule. So we bring the power down, subtract 1 from the exponent, keep the inside function the same, which is sine x. Then you have to multiply by the derivative of sine, which is cosine. And for the bottom, you have to use product rule. The derivative of x is just a 1. To keep the second function the same. Then plus, keep the first function the same, and multiply by the derivative of cosine, which is minus sine. And that's why I have the minus sign over here. Now let's try to evaluate the limit once again. When you plug in 0, the top is going to be 0 because sine of 0 is 0. So the entire thing is just 0. Now on the bottom, you have this term being 0 because of the x and sine x. And cosine of 0 is just 1. So 1 minus 0. So great, this is no longer indeterminate. We have 0 divided by 1, which just evaluates to 0. Now we can go back and plug the answer into this limit. We found the answer being 0, so the answer is e to the 0, which evaluates to 1. And so therefore the value of the original limit is just 1. And lastly, as I promised, I would explain why something like infinity to the 0 is an indeterminate power, but something like infinity to the infinity is not. It's a determinate power. And so let's see how to reason about that. If you recall, our goal was to evaluate a limit of the form as x approaches a of f of x to the g of x. And the way we did that was we wrote this in terms of e and ln, then we brought the exponent down, we passed the limit sign through the exponential, and we got to this final form. And we talked about how to evaluate this limit, it boils down to evaluating this sort of product. And so the limit actually depends on this limit. And so let's analyze this exponent. Now I have convinced you before of why something like 0 over 0 and infinity minus infinity are indeterminate by giving you examples, right? I can give you different functions that have this form but evaluate to different limits or sometimes don't exist, and that shows that something is indeterminate. In this case, I'm going to employ a different approach. Instead of giving you concrete examples, I'm going to try to reduce this into a known indeterminate form, specifically 0 times infinity. And that will also end up showing that these forms are indeterminate. So let's take a look at what I mean. So let's suppose you're trying to evaluate this limit and you're running into this form 1 over infinity. What does that mean? Well, that means that the base is approaching 1. So the limit as x approaches a of f of x is just 1. And the exponent is approaching infinity, right? The limit as x approaches a of g of x, this thing is basically approaching infinity. Well, if you reason about what's going on in this product, check this out. We have the limit as x approaches a of g of x times the natural log of f of x. We know this is going to infinity. We know f of x is going to 1. And what's natural log of 1? 0. So this thing is going to 0. So we have infinity times 0. And infinity times 0 is a known indeterminate form. And that shows that 1 to the infinity is also indeterminate. Similarly, we can show the other two powers are also indeterminate. So let's suppose you have the form 0 to the 0. That means that the base and the exponent are both approaching 0. And now let's consider this exponent limit that we've been looking at. So g of x is approaching 0, and then f of x is approaching 0, right? But as you approach 0, from the right-hand side at least, natural log will approach minus infinity. And so as a result, we have 0 times minus infinity, which is again an indeterminate product. That's why 0 to the 0 is indeterminate. And lastly, if you have infinity raised to the 0th power, then the base is approaching infinity, and the exponent is approaching 0 as your inputs get closer and closer to the limiting value a. And now let's reason about the exponent limit, the limit as x approaches a of g of x times the natural log of f of x. So g of x, as you can see, is approaching 0, and then f of x is approaching infinity, and natural log of infinity is going to also be infinity. So we have again 0 times infinity, which is a known indeterminate form. And this shows that infinity times 0 is also indeterminate. And so this is what I mean. When you're working with these limits of powers and you end up running into these sort of indeterminate forms, they're indeterminate forms because they lead to this exponent limit being an indeterminate product. Now lastly, let's show why something like infinity to the infinity and 0 to the infinity are not indeterminate. They're actually determinate powers. Whenever you see something like this, a form like this, you will actually already know what the answer is. So the idea is similar. Let's suppose that we have infinity to the infinity. So that means that both the base and the exponent are approaching infinity as the inputs approach their limit point. And then if we analyze the behavior of the limit in the exponent, then we have that g of x is approaching infinity, f of x is approaching infinity, and natural log of infinity is also infinity. So we have infinity times infinity. This is not indeterminate, right? The answer is just infinity. And so now be a little bit careful because this doesn't represent the value of the original limit. For the original limit, we have to take e to this answer, right? We have to take e to this answer. So the value of the original limit is e to this answer, which is sort of like e to the infinity, right? So this number basically keeps growing without bound. And when you take e to like a very big number, it's also going to keep growing without bound. So as a result, whenever you encounter this form in your powers, limit of a power, the answer will always just be infinity. Similarly, let's take a look at the form 0 raised to the infinity. In this case, the base is approaching 0, and the exponent is increasing without bound as your inputs approach your limit point a. So again, upon analyzing the behavior of the limit in the exponent, what we see is that g of x is approaching infinity, and f of x is approaching 0. But natural log, as you approach 0, it's going to approach its asymptote. So it's going to go to minus infinity, at least from the right-hand side. So we have infinity times minus infinity, right? Infinity times minus infinity. And that is not indeterminate. It just equals minus infinity. You're multiplying two very large numbers together. One of them happens to be negative. So you're going to get a very large negative number. And now check this out. The value of the original limit, which is the limit of this power, right, that you're working on, is going to be e to that answer, right? It's going to be e to whatever this answer we got was. And this answer was minus infinity. Now, if you look at the graph of e to the x, then as the inputs approach minus infinity, e decreases, right? E actually decreases and approaches its asymptote, y equals 0. And so e to the minus infinity is equal to 0. So this will basically approach 0. Again, this is a little bit loose notation here, just to show you the idea of what's going on. But the idea is that when you have this form, 0 raised to the infinity, then the exponent just decreases without bound. And e to a very tiny input will approach 0. And so whenever you're working with these sort of limit questions involving powers, and you come across this form, you actually don't have to do any work. The limit is just going to evaluate to 0. If you don't recognize that, that's okay. You can go ahead and try to evaluate the limit using the regular techniques we saw above. You'll end up seeing that the answer will evaluate to 0 anyways. Okay, awesome. And so that brings us to the end of today's video, in which we covered indeterminate powers and how L'Hopital rule does not apply directly to evaluate these indeterminate powers, but using some clever ways, we can convert it into an indeterminate product, and then we know how to convert an indeterminate product into an indeterminate quotient, and then apply L'Hopital's rule. And then also in today's video, we discussed why some powers are indeterminate, whereas some aren't, and we reasoned about it very nicely without examples. Instead, we reduced it to a known indeterminate form. This also brings us to the end of this small series of videos on L'Hopital's rule. We've covered all the indeterminate types along with their examples. Now, if you're interested in looking at some more examples or even some more tricky examples, then I already have some videos published on tricky L'Hopital rule examples, which you can view after this. And so thank you for watching. I'll see you next time. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.